On the screen in front of you are passageways leading deep into far Earth, to a world inhabited not by elves, dwarves and hobbits, but by even stranger beings, quarks, leptons, bosons. This chapter of your life will be getting to know a little of what far Earth is like, based on the stories of those who have ventured into it and returned. And then, if you are brave enough, you can continue your search for the inhabitants at a later date. But beware, there are some rules of entry you have to obey before venturing into this dark and threatening land. You have to allow your mind to be stripped of all preconceived ideas of what the world is and how it works. And above all, you must give up your desire that everything makes sense, and your need to be able to explain the unknown in terms of the known. Listen to what Hobbit Heisenberg had to say about this. The problems of language here are really serious. We wish to speak in some way about the structure of atoms, but we cannot speak about atoms in ordinary language. These explorers of the early 20th century had ventured into far Earth and were both exhilarated and terrified by what they saw. But when they came back and tried to describe it, words failed them, as Heisenberg is pointing out here. They needed a new language, but no such language exists, because language is based on our everyday experiences, and these have little in common with what happens in far Earth. Just as Copernicus, Kepler and Galileo had done before them, these brave explorers of the 20th century dared to think differently. Those early pioneers had refused to be constrained by either what was accepted as true or what seemed self-evident, that the sun orbits around the Earth. They started a revolution, and others like Newton followed to give it a firm foundation. Maxwell added to it with his wonderfully coherent treatment of electromagnetism. But by about 1900, even this great new understanding was not able to explain some strange phenomena, such as the spectra produced by the different elements, the photoelectric effect, and the diffraction of electrons. A new world was beckoning, and a new science had begun. It was 1897 when a brief sighting of far Earth was made, without anyone realizing at the time where this would take them. J.J. Thomson was experimenting with a cathode ray tube, without quite knowing what these cathode rays were. He put them in a magnetic field and saw that they were bent, the rays were bent. From that he deduced that the rays were actually made up of tiny particles, and from the amount of bending he could calculate the mass and the charge of these particles. Their mass was much smaller than the mass of an atom, and they were negatively charged, he found. And thus the electron was discovered, the first subatomic particle. But what would these early explorers do with it? How would they understand it? Was it part of the atom or something outside the atom? The next breakthrough was just as remarkable. Thomson had discovered the electron, and in 1909 Rutherford performed the famous gold foil experiment and discovered empty space. Oh, and the nucleus. So the plum pudding model that Thomson had put forward gave way to the planetary model, where electrons were seen as orbiting around the nucleus. But soon this was seen to have shortcomings too. It could not explain the spectra from individual elements, and nor could it explain how the electron managed to stay in its orbit without collapsing into the nucleus. Niels Bohr came up with the idea of energy levels to get around these problems, the idea that the electrons could only exist in fixed, predetermined energy levels. These explained the observations, but why they should exist at all was not known at the time, and what determines the amount of energy in each level. They would have to wait some years for a theoretical explanation of these energy levels. But for now, a quantized understanding of the atom was emerging. Meanwhile, there were other troubling findings that needed some rethinking to explain them. Back in the 1600s and 1700s, Newton believed that light was made up of particles, but the influential work of James Maxwell in the 1800s explained electromagnetic phenomena in terms of waves. But around 1900, experimenters discovered something that challenged this, the so-called photoelectric effect. The observation that, under certain conditions, when light is shone on a piece of metal, a small electric current is produced. This could not be explained using classical wave understanding of light. It was Einstein in 1905 who managed to explain it satisfactorily, and he used a quantum understanding of light to do it. So the photon was born, and the quantization not just of the atom, but now even of light, continued its unstoppable march. But there was another side to this. While Einstein had shown that light, which was known to have wave-like properties, was quantized into particles of energy, or photons, in 1927 an experiment showed that electrons behaved as waves. In the electron diffraction experiment, we get interference patterns consistent with wave theory. So the distinction between waves and particles is getting very blurred, and trying to describe far Earth in terms of near-Earth objects, waves and particles, is becoming very difficult. De Broglie had already come up with the idea that if waves could behave like particles, perhaps matter could also be thought of as waves. He first published his theories in 1924. De Broglie's ideas helped explain why electrons could only exist in certain orbits, according to their wavelength fitting in with the parameters of that orbit. So this explained Niels Bohr's ideas of energy levels being fixed. De Broglie then seemed to be completely vindicated with this wave idea of matter by the electron diffraction discovery in 1927. So now wave mechanics had been born, and this new baby was nurtured by Heisenberg with his famous uncertainty principle and Schrödinger with his famous cat and his wave equation.